session of the Round the World Relay. Pretty cool to end it with a bang. I would like to introduce our speaker, Ron Gould, who's the Goodrich White Professor at Emory University. He's emeritus now, but as we have been saying, he's only retired from the grind of faculty membership like service, not from research. He's published numerous papers and had, I think, 28 PhD students at this point.
Yeah.
Yep. And I won't admit that I was one of them because that might give away his age.
I'm going to give it away in the talk.
Anyway, he'll be talking to us on chorded cycles.
Thank you, Jill. And thank all of you who are still hanging around. You are strong people, and I'm proud of you. So I'm going to talk today about a problem that should have been solved, or problems that should have been looked at decades ago, but weren't. So we're going to say a chord is an edge between...
Sorry to interrupt. Jill, would you like start recording? Yeah, sorry to interrupt.
Thank you for the reminder.
Okay, we okay now? All right, so chord is just an edge between two vertices on a cycle that's not an edge of the cycle. It's just what you think it should be. And back in 1960, Posa posed a question: what conditions imply a graph contains a cycle with a chord? Posa was 12 at the time when he posed this question. I was 10, and I wasn't posing any questions. So he was a little ahead of me. Now there's our chord. So we're going to say that a cycle is chorded if it has at least one chord. And for some reason, I don't know if you can see the top line, I can't on mine, but Zipser in '63 was the first to answer Posa's question. And a graph that has minimum degree 3 is going to contain a chorded cycle. And I call this a theorem. It's really just an observation. If you just take a longest path, look at an end vertex, it has to throw at least 2 edges back, there's a chorded cycle. So that wasn't exactly too hard to come by. But that little observation is not so bad in the long run, as we'll see. All right, so some notation that I'm going to be using throughout a lot of this. Sigma sub k of g is going to be the minimum degree sum, where that minimum is taken over all sets of k independent vertices. Sometimes, especially when k is 2, people call this the Aura degree condition, from Aura's famous Hamiltonian theorem. All right, so everybody jumped on the chorded cycle research problem bandwagon 45 years after Zipser's observation. Finkel came up with the following: that if G is a graph on at least 4K vertices with min degree at least 3K, then G is going to contain at least K vertex disjoint chorded cycles. Now, that's a nice theorem. His proof technique is fairly standard. It's the maximum counterexample type technique that you would see a lot in cycle problems. But the reason I really like this result is the following. If you look at the old famous Karate-Heinel theorem, let G be a graph with order at least 3K and minimum degree at least 2K, then G contains K vertex disjoint cycles. So you can look at Finkel's theorem as an extension of Karate and Heinel in very natural ways. Min degree 2, we all know, implies there's a cycle in the graph. We just saw that min degree 3 implies there's a chorded cycle. You need at least 4 vertices to have a chorded cycle. You need at least 3 vertices to have a cycle. Multiply all of those things by K and you got these 2 results. They just fit in a very nice way together. So that's why I think Finkel's theorem is an especially nice way to start your introduction into this area. Okay, as I already said, we need the 4K vertices because each of the K cycles needs at least 4 vertices. And this condition is sharp. Just take a bipartite graph with 3K minus 1 vertices on one side and all the rest on the other. And I don't know if on your slides, but mine, the bottom end minus 3K plus, it should be a +1, but it's not showing up on my slide for some reason. Anyways, simple graph to show that his degree condition is sharp. There just aren't enough vertices in the small set because to build chorded cycles in a bipartite graph, you need 6 cycles at least. All right, Bielostocki, Finkel, and Jarfas looked at another chorded cycle problem. They defined Fn to be the minimum number of edges in a graph of order n that ensures the graph contains 2 vertex disjoint cycles, at least one of them chorded. They also defined a Gn where it would be both of them are chorded. And they were able to show for n at least 10, Fn is 4n minus 5, and for n at least 12, Gn is 5n minus 24. Now, it remains open to determine the minimum number of edges in a graph on n vertices, ensuring k greater than or equal to 3 disjoint chorded cycles. That's an interesting open problem. I must admit, I have not put any time in on it. Answering another conjecture of Bielostocki, Finkel, and Jarfas, the following result: let R and S be integers with R plus S at least 1, and G a graph of order at least 3R plus 4S. And you'll see in a second why you want those numbers. If sigma 2 is at least 4R plus 6S minus 1, then G contains a collection of R plus S vertex disjoint cycles such that S of them are chorded. Well, obviously, the 3R is for the cycles that aren't chorded, and the 4S is for the S cycles that have to be chorded. You need at least that many vertices, so that's clear. And this is really just an extension of what we've seen already in terms of what the degrees need to be. Sharpness example, same thing. You just play with a bipartite graph and you partition it so the small side is just 1 short of what you need. And that's common in a lot of these examples. There were 2 different groups that proved this following theorem. And the reason I put it in is just for its form. Let k be a positive integer and G have order at least 4k with our sigma 2 condition at least 6k minus 1. Then G contains k vertex disjoint chorded cycles. I'm a little surprised both these papers got through because they're both corollaries of this. But they all came out at about the same time, so I think there was enough confusion going on, or at least enough lack of people knowing what was happening at the time, that both of these papers got out. All right. With Kazuhiro Hara and Ariel Keller-Rohrbach in last year, we were able to extend to sigma 3 and show that if G had order at least 8k plus 5 and sigma 3 is at least 9k minus 2, then G contains k vertex disjoint chorded cycles. All right, so we got a little bit of a pattern going here. With the minimum degree from Finkel's theorem, 3k implied k disjoint chorded cycles. Then we saw sigma 2 was at least 6k minus 1 to get k disjoint chorded cycles. Sigma 3, 9k minus 2. From there, you should guess that sigma 4, 12k minus 3, and that's true. We proved that already. And also at the end of last year, with Brad Elliott and Kazuhiro Hara, we were able to show if n was big enough, and that number I'm sure is not best possible. If sigma sub t is at least 3kt minus t plus 1, then our graph had to contain k vertex disjoint chorded cycles. Further, this degree condition is sharp, and you can guess that the sharpness example is a bipartite graph again. The 8k squared minus 9k plus 12t plus 1 is an artifact of the proof. We didn't think it worth the major effort to try to knock that down any further. So we just let it go at that. Okay. Well, along the same lines, I'm going to say that a cycle is doubly chorded if it induces at least two chords. So always, whatever I say, chorded, at least one chord, doubly chorded, at least two chords. And a theorem with Paul Horn and Kazu Hirahata is the following. If you use a graph of order at least 6K with sigma 2 at least 6K minus 1, remember you've already seen that implies K disjoint chorded cycles. Well, we were able to show it really implied K vertex disjoint doubly chorded cycles. The proof of this is much, much harder than the single chord case. There are many, many lemmas we needed to prove about the interaction between paths and cycles with edges between them in various ways. And that caused us a lot of technical difficulties, but we were able to overcome them. Okay, so let's reminisce about the old days. Back in '71, Bondi noted a relationship between the conditions of the number of edge density results on Hamiltonian graphs and those of pancyclic graphs. Now you have to remember that back in those days, pretty much all Hamiltonian results were based on edge condition, or I'm sorry, degree conditions of some sort. The aura type result, the Dirac's mean degree condition, and there were a series of other results on degree sequences where they satisfied certain conditions to get cycle results. So those were the kinds of things he'd seen at the time. And in one of his papers, he posed what came to be known as Bondi's meta-conjecture, that almost any non-trivial condition on a graph, which implies that the graph is Hamiltonian, also implies that the graph is pancyclic, but there may be some simple family of exceptional graphs. And we'll see right now why he made that last statement. If you think back to Aura's theorem in 1962, that sigma 2 at least n, then G is Hamiltonian. In '71, to support his meta-conjecture, Bondi showed that if sigma 2 is at least n, then G is pancyclic, or it's the complete balanced bipartite graph. So there's his family of exceptions. Well, with Megan Cream and Hirahata back in 2017, we decided to extend Bondi's meta-conjecture that almost any condition that implies the graph is Hamiltonian also implies it is chorded pancyclic. That is, contains chorded cycles of every length from 4 to the order of the graph. There may be some simple families of exceptional graphs or some small order exceptional graphs. And of course, we're saying almost any condition. It's not hard to find conditions that don't do this. But what we were able to show was that if we had the sigma 2, at least n, the aura type condition on Hamiltonian graphs, then G is chorded pancyclic, or it's the complete balanced bipartite graph, or it's this graph that I call G6, which is K3, a Cartesian product with K2. And there's G6 drawn two different ways. And it's pretty easy to see, especially with the right-hand drawing, that there's no chorded 4 cycle in that graph. So that would be the problem. The degree condition, as you might remember from Aura's theorem, is sharp if you just take two complete graphs that share a vertex. Then that graph's not Hamiltonian and just misses the degree condition. And if you also take the complete balanced bipartite graph and add one edge to either partite set, then that's going to be chorded pancyclic, but not doubly chorded pancyclic, as no 4 cycle contains 2 chords. So that's something that's kind of important to note for later on, because mostly I now think that my metaconjecture ought to be on doubly chorded cycles instead of chorded cycles. But chorded is more likely to happen because of this. All right, Bondi also in 71 supported his metaconjecture with another result that said every Hamiltonian graph of order n with at least n squared over 4 edges is pancyclic.
Recording in progress.
Unless n is even, and G is the complete balanced bipartite graph. And in particular, if there are more than n squared over 4 edges, then it's pancyclic. But remember, you got to be Hamiltonian to start with. Well, back in 2018, with Chen, Gu, and Saito, we were able to show that if G is a graph of order n with at least n squared over 4 edges, and k is a positive, and let k be a positive integer, if G contains a k cycle, then it contains a chorded k cycle, unless k is 4, and G is either the complete balanced bipartite graph, or our old friend G6 here, K3, Cartesian product, K2. And extending Bondi's theorem, using our theorem above, we get the following corollary, that a Hamiltonian graph of order n at least 4 with at least n squared over 4 edges is chorded pancyclic, unless it's one of those two exceptions. So that's a combination of Bondi's result and our theorem. All right. Unfortunately, let me see if I can move this. Yes, I can. Let's put this down here. Gowland and Wang in 2019 came up with a bipartite result that, given a balanced bipartite graph where each partite set has at least 3k vertices, if the minimum degree in this graph was at least 2k plus 1, then G was going to contain k vertex disjoint doubly chorded cycles. So that was really the first result that concentrated on trying to do something inside bipartite graphs. Okay, so let's go back to more on degree sum type results. So back in the previous century, with Brandt, Chen, Faudree, and Lesniak, this was a crazy result because we just decided to hang around in Memphis after a conference, and we sat around one Saturday and proved this. So let k be a positive integer and G a graph of order at least 4k. Take the standard aura degree condition, sigma 2 at least n. Then G has a 2 factor with exactly k vertex disjoint cycles. And again, it's the bipartite graph that's the limiting factor, because there you need 4 vertices in each of the cycles, so that's where the 4k comes from. Well, very recently, Chiba, Jiang, and Yan showed the following result. So select your favorite positive integers k and c. Then there's another integer f that depends on k and c, so that if G has order n at least f of kc and sigma 2 at least n, just the aura condition, then G can be partitioned into k vertex disjoint cycles, each of which has at least c chords. So they, in a sense, extended my result with Brandt, Chen, Faudree, and Lesniak, where they knew they had the k cycles to start with, and they were able to show that if things are big enough, you're going to get as many chords as you want to put in each of those cycles. Not a major surprise when you think about it, but still kind of a nice result. And it's the only result I know of right now where you pick how many chords you want exactly, and you go for it. Well, that's not quite true. I know another one, but I'm not sure we'll get that far in this talk. All right, why is my page not turning? There we go. All right, so I'm going to use the notation that n of x, y is just the union of the neighborhood of x and the neighborhood of y. And you can think of it as a density condition that opposes the degree sum condition in that the common overlap vertices are only counted once, not twice like in degree sums. So back in 2010 with Hirahata and Horn, we were able to show if n was at least 4k as usual, such that for any pair of non-adjacent vertices, n of xy was at least 4k plus 1, then our graph is, that h should be a g, contains at least k vertex disjoint chorded cycles. So a simple neighborhood condition getting k vertex disjoint chorded cycles. I'm going to conjecture that that same degree condition ought to give us k vertex disjoint doubly chorded cycles. And I will admit that I have tried to prove it and failed so far. Thought I had it once, and then on closer examination, there was one point that just I have not been able to push through, and I actually haven't looked at for months now. So maybe when I go back, it'll work. Okay, another question. The same kind of question's been looked at just for cycles, so it's natural to ask, when can we have many chorded cycles of the same length? So, again, let me move this. With Chen, Hirahata, Oda, and Song back in 15, we were able to show that for a natural number k, there exists a positive integer n that depends on k, such that if G is a graph with min degree at least 3k plus 8 and order at least n sub k, then G is going to contain k vertex disjoint chorded cycles of the same length. This is similar to a result of Verstraet's about just cycles. And another thing that we were able to show was if I took a multigraph of order n with minimum degree at least 5, then G is going to contain a chorded cycle of length at most constant log base 2 of n, where this constant sits somewhere between 30 and 300. All right, so other questions that are natural to ask is, when can we make an independent set of k edges, the chords of k vertex disjoint cycles? Okay, so with Cream, Faudree, and Hirahata in 2016, we looked at this question, and we were able to show for n big enough and sigma 2 at least n plus 3k minus 2, then any k independent edges in the graph, we can find our k vertex disjoint cycles such that the EI is a chord of CI for all the i's equal 1 to k. What surprised us was we were further able to show that we could make all those cycles small. They were either 4 or 5 cycles. Well, if I can place edges in places, maybe I can place vertices in places. So another question would be, when can we distribute k vertices on k disjoint chorded cycles? So with Cream, Faudree, and Hirahata, again, same paper, we were able to show for n big enough and min degree at least n over 2, then any set of k vertices, we could find a collection of k vertex disjoint chorded cycles, C1 to CK, such that vertex VI had to be a vertex of the cycle CI. And again, we could make the cycles reasonably small. They're no bigger than 6 cycles. Well, if I can place vertices, can I place edges? And the answer, of course, is yes, or I wouldn't be talking about it. So again, if n is big enough and I take k independent edges, E1 to EK, with minimum degree at least n plus 2k minus 2 over 2, then there's going to be a system of k chorded cycles such that EI is an edge of the cycle, not a chord, but an edge on the cycle itself, even though the cycles are chorded. And again, we can make the cycles all small, at most 6 cycles. So as a corollary to the proof, we obtain the fact that the edges E1 to EK can actually be mixed. They can either be chords or edges of the cycles. Once again, 1 per cycle. So I can mix and match them as I want. Further, we can show that the cycle system that you produce, which was small cycles to begin with, can also be expanded so that they actually span the entire vertex set. That's an old trick. Once you got enough of a degree condition in with cycles, you can usually do things like that if you try hard, or in fact, not so hard. Okay, so let's talk doubly chorded cycles. So again, order big enough and K independent edges. If my minimum degree is at least n plus 2K minus 2 over 2, then there's a system of K vertex disjoint doubly chorded cycles such that EI is a cycle edge and not a chord, but a cycle edge. And again, the cycles are all small cycles, less than or equal to 6 in order. And a corollary, get this damn thing out of the way. Again, we can extend these cycles to span the entire vertex set because that degree condition is plenty big. Okay. Well, once you start putting edges on cycles, it's really not that hard to start thinking about paths. So given an independent path system, PR1, PR2 up to PRK, where PRI means a path with RI vertices. And in each of those RI is at least 2. We're just going to let R be the sum of those RIs. Then the number of interior vertices in this path system is quite obviously just R minus 2K. Right, I lose the 2 end vertices for each of the paths. So that's the trivial observation. Now with Cream, Faudree, and Hirahata, we were able to show that if n's big enough, and I have a minimum degree n over 2 plus r minus k minus 1, and I let P1 through PK be any k independent paths in G, then there exists k disjoint doubly chorded cycles D1 to DK, such that DI contains the path PI as a path along the cycle, and the cycles themselves are bounded in order between Ri plus 2 and Ri plus 4 in size. So they're not all that much bigger than the path I forced onto the cycle. And again, this is really a function of the fact that this is a goodly sized minimum degree condition. Okay, let's talk forbidden subgraphs. So I'm going to use the notation K13 for what is often called the claw. Z2 is this triangle with a 2 path off of one vertex. And P4, we've already talked about, a path with 4 vertices. These are very common forbidden subgraphs in cycle results. All right, back in '97, Ralph Faudree and I were able to show that if R and S are connected graphs, and G is not a cycle, but a 2 connected graph of order at least 10, then the statement that G is RS free implies that G is pancyclic if and only if one of the graphs is the claw, K13, and S is one of the graphs, path on 4 vertices, 5 vertices, or 6 vertices, or Z1 or Z2. Z1 is just the triangle with one edge off of one vertex. All right, so we were able to characterize the pairs, the forbidden pairs for 2 connected graphs that implied the graph is pancyclic. So we decided to look at that same problem for chorded cycles. So with Megan Cream and Victor Larson, back in 2017, we were able to show that if we started with a two-connected graph of order at least 10, and G is CLA and Z2 free, so that's one of our pairs for pancyclic to begin with, then either G is the cycle CN or G is chorded pancyclic. So that says it has chorded cycles of all lengths from 4 up to the Hamiltonian cycle. All right. Now going back and looking at the paths, we were able to show that CLA P4 free implied chorded pancyclic if n was just 5 or more. And if n, we took n up to 8, then we could take the path up to a P5. If we took n up to 13, we could take the path up to P6. So just making the graph big enough, any one of the pairs that we saw for pancyclic would give us chorded pancyclic. All right, some other extensions of cycle results. Let me have a little drink here. You know, the nice part about a Zoom talk, if you're holding a coffee cup and you blow on it, people actually think there's coffee in the cup. All right. Back in 1990, my old friend Hendry was able to show that minimum degree at least n plus 1 over 2, then the graph was going to be vertex pancyclic. And by that, I mean each vertex appears on a cycle of each length from 3 to n. So that's a pretty strong statement. But then again, that's a strong minimum degree condition. Well, again, with Megan and Kazu, we were able to show that you take those same conditions with n at least 4, then G is chorded vertex pancyclic. That is, each vertex appears on a chorded cycle of each length from 4 to n. So that, again, back to the meta conjecture, here's a condition that gives us pancyclic, and we take it to chorded vertex pancyclic. And we were also able to show that there's with minimum degree n over 2, there is a doubly chorded K cycle in G containing X for any K at least 5. So that says G is chorded 5 actually it should be doubly chorded 5 pancyclic. Ronderoth et al. Back in 2002 had another vertex pancyclic type result where the sigma 2 was at least n plus 1 more than the aura condition. Then they were able to show that G was vertex 4 pancyclic. So any vertex is on a cycle of length 4 on up to a Hamiltonian cycle. We were able to take exactly the same sigma 2 condition and show that then G is chorded vertex 5 pancyclic. So every vertex is on a chorded cycle of length 5 on up to the Hamiltonian cycle. There are examples where, I believe we had an example where there was no, there was a vertex not on a 4 cycle. All right, Ronderoth also showed if sigma 2 is at least the ceiling of 4n over 3 minus 1, then G is vertex pancyclic. We took the same condition and showed that G is chorded vertex pancyclic, just had to make n at least 8 instead of 3. So far, what I've been showing you fundamentally says, find your favorite cycle result and turn it into a chorded cycle result. So here's what I consider the most interesting of the questions. How many chords should we expect or hope to find? Pretty much all we've talked about so far, except for one case, is either a chorded cycle or a doubly chorded cycle. Well, let's consider a special case here cliques. I can always look at a Hamiltonian cycle in the clique, like this blue cycle in this K5, and I can consider all the remaining edges as chords of that cycle. So in general, given a K sub K plus 1, then we know that graph is K regular. And if you just do the count, we're going to set f of k equal to k minus 2 times k plus 1 over 2. That's how many chords are in these cliques. So we want to think of f of k chorded cycles as kind of what we call loose cliques, loose k sub k plus 1s. So maybe there are more than k plus 1 vertices, but I get this special number of chords. Okay. So, as is obvious here, there are no single chorded cliques. That doesn't say much. But Ollie and Staten back in '99 showed that if the minimum degree of G was K, then G would contain a ceiling of K times K minus 2 over 2, a chorded cycle with that many chords, K times K minus 2 over 2. Now let's compare that back to this thing. So our function is a K plus 1 times the K minus 2. Theirs is just a K. And as a corollary, if G had min degree 3, then G contains a doubly chorded cycle. So that strengthens the Zipser observation that we started the talk with. He had min degree 3, he meant a chorded cycle. Their result says there has to be a doubly chorded cycle. In my terminology, a loose K4. All right, with Paul Horn and Colton Magnet, our first step was the following theorem. If we had minimum degree K, then G actually contains an f of K chorded cycle. So a strengthening of the Ollie-Staten result. The proof looks a lot like what I showed you from the Zipser observation. Start with the longest path. Only start with not just a longest path, but a longest path whose end vertex throws the furthest possible chord. And now think about the vertices that precede where the chords land. Those are also first vertices of longest paths. I'm sorry, I did that wrong, this way. Back down and then on out. So where do their edges go? Their edges all have to go in here. So if you carefully count how all these edges land, and you have to make sure you're not double counting, that's the key issue, you end up with this result. So that initial Zipser observation came in handy here. All right, so why did we want to think about this? Well, there's the famed Heinel-Zimmeretti theorem from 1970 that I'm not going to do as a coloring theorem, but as a partitioning of cliques. If the minimum degree is at least KT, and the order of G is K plus 1 times T, then G can be covered by T vertex disjoint K sub K plus 1s. All right, that's a famous theorem. It's a beautiful theorem. What we were hoping for was a loose version of the Heinel-Zimmeretti theorem, where our order did not have to be exactly this, but just greater than or equal to this. So our conjecture is that if the minimum degree is at least KT and the order is at least K plus 1 times T, then G contains T, f of K, disjoint chorded cycles, where this is our f of K. The tight end is the Heinel-Zimmeretti theorem. If T equals 1, this is our first theorem. So we show it's true for some classes of graphs and for graphs with some extra room with this theorem. So there exists a K sub 0 and a T sub 0, such that if the min degree is what we asked for, and K is at least K0 and T is at least T0, and N is big enough, a function that depends on the k and t. Then G contains T disjoint cycles with at least f of k chords. So this is a loosening of the Heinel-Zimmeretti theorem in a sense that we are looking for cycles without that clique number of chords. And if we make things big enough, it will work. This doesn't cover all cases because the K0 and the T0 have a little fight in the proof. They work against each other a little bit, so it's not quite covering all cases, but it's covering a lot. And I guess I'm pretty close to end of time, so this is probably a good spot to end. So I'll stop here and see if there are any questions.
How about if we begin by thanking our speaker, so you can unmute and clap. And now I'll see if there are any questions.
Okay, I guess not. Then you can go home and go to sleep.
So Ron, would you go back to, God, is a horrible question. Go back to the very beginning. So I think you said that one of the open questions is an edge density question. Is that right?
Yeah. Here, this is what you mean.